Cool. All right. So this is where the last slide ended up for last week, not Tuesday, but previous week. We ended last week on Ohm's law. And then this week, we started to expand on Ohm's law with this slide. And on this slide, pull out your calculators because I want to reiterate these Ohm's law calculations with you, okay? And it doesn't matter whether you have a Sharp or whether you have a Casio or whether you have a Hewlett-Packard, doesn't matter. These are very basic calculations. The important thing is I want you to recognize how to read Ohm's law. And as you read the symbol, in this case, instead of a circle, we're showing triangles in this particular case. And what it is that you see is V above the horizontal line, and then you see a vertical line between the I and the R. The horizontal line, if you recall, represents the math function of division, and the vertical line between the I and the R represents multiplication. So if you have any two of three quantities, you can calculate a third quantity. So if we take a look at the numbers that are given, the very first one, if we say R is equal to 2 ohms and I is equal to 4 amps, you are asked to calculate V. You look at the options in front of you, and you see V is equal to what? I times R, yes? So you have an I times an R. The value of I in this case is 4 amps. The value of R in this case is 2 ohms. 4 amps times 2 ohms gives you how many volts? 8 volts. Pretty straightforward so far, yes? In the second line, if your voltage source is given 8 volts and your R1 is given as 2 ohms, you are now asked to calculate for I. And as you look at the triangles, the middle triangle and the formula right underneath it gives you the formula for I. I would be equal to V divided by R. The V in this case is 8 volts, divided by the R of 2 ohms. So 8 divided by 2 gives you how many amps? 4 amps. So one more, and the last bullet point here shows voltage source. If the voltage source above is 8 volts and the current is given as 4 amps, you are now asked to calculate for R. You look at the triangles again, and then you see, you're able to see that R is equal to V divided by I. That being said, your V of 8 volts divided by I of 4 amps gives you 2 ohms. The easiest thing for many students to miss is this. They miss out on writing down the electrical symbol. If it's voltage, it should be V for volts. If it's resistance, it should be the omega for ohms. And if it's current, it should be A, capital A, for amps. A lot of students are so focused on popping in the number. Oh, we're so excited about getting the number. Here, I got a number. I'm going to write down the number. We have to remember from this point forward, the number plus the engineering prefix plus the electrical symbol are critical, okay? Next slide. We're talking about in resistor color coding. We talked about that this past Tuesday. And in resistor color coding, we have 4-band resistors, 5-band resistors, and this goes to reiterate how to play with the color bands. What I want to focus our attention on, this first slide here emphasizes the 4-band resistor color code. So you're given orange, violet, brown, silver. So orange is 3, violet is 7, brown being the 3rd band tells you number of zeros, and I highlighted that in yellow, number of zeros. So 3, 7 followed by a single 0 is 370 ohms. And then you look at the tolerance, and tolerance means what? Tolerance means degree or margin of error. When they go to make these resistors, they make them like baking a cake. And sometimes the mix has a little more of this, a little less of that. And so there is going to be some margin of error. And so in this case, silver indicates plus or minus 10%. The coded value is shown. The resistor coding for 5-band resistors are done here. Done on this slide. This is on the 5-band resistors. And we decoded this. So you have yellow, gray, green, yellow, and red. So the first 3 bands are the first 3 digits. First band, yellow, the digit is a 4. Second band, the color is gray, the second digit is an 8. Third band, the color is green, the value is going to be a 5. The fourth band, and I highlighted this in yellow, number of zeros. It's easy for us to remember that multiplier band You could think of the multiplier band as 10 power of 4, or just simply add 4 zeros to the first 3 digits. And then the fifth band tells you the tolerance, and in this case, being red, the tolerance is plus or minus 2%. So the bottom line here is the coded value works out to be 485 followed by 4 zeros plus or minus 2%. If you put in the commas, it becomes a little easier to read, 4,850,000 ohms plus or minus 2%. But we had an agreement of rounding to 2 digits after the decimal point and expressing our quantities in proper engineering notation. 7 digits in front of the decimal point is not proper engineering notation. I've had some people show the answer as 4,850 kilo ohms. Well, 4,850 kilo is still 4 digits in front of the decimal point. No bueno. So if you take your handy dandy calculator, we take our handy dandy calculator and we go to key into our handy dandy calculator 485, and then followed by 4 zeros, ding, 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 ding. And then you hit enter, you get some scientific, actually this worked out, and it shows you 4.85, and it shows you a 10 power value on the right-hand corner. What is that 10 power value? It should be 10 power of 6. And you should have in your wonderful book, which you can use, as I said, on any quiz, any test, you can use this guy. You should have in here your engineering prefixes copied into this notebook, and you can just use it as reference anytime. So you look up 10 power of 6, and that is mega. So we have mega. Next, tolerance. Resistor tolerances, this is an expanded discussion on resistor tolerance, this particular slide, and it goes to show how you are able to determine maximums and minimums very quickly. So if we take a look at the yellow box, oops, come back here. In this slide, the yellow box, the white box is a reiteration of your color codes. It's a reiteration of the color sequence and the numeric values assigned to the colors, and then the tolerances depending upon where they're used. So if we take a look at the yellow box shows you red, white, brown, and silver. So that is a 2 and a 9 for the first 2 digits. The third digit is a what? It's brown. It's not a third digit. What does the third band represent in this particular case?
Number of zeros?
Number of zeros. And brown tells you there's 1 0. So you have a 2 and a 9 followed by 1 0. You've got 290 ohms, plus or minus 10%. The measured value, and a number of you started to make measurements very nicely on the circuit builds that you've turned in so far, very nice. And the measurement won't be exactly 290 ohms in many cases. There's going to be some percent of error. There's going to be some number of ohms off of the coded value. So how do we calculate how low it can be, which is the minimum? How can we calculate how high it can be, which is the maximum? The way that you calculate the minimum, if you take a look at this, what is 10% of 29? Whack a 0, take off a 0. I'm sorry, I didn't say it right. What is 10% of 290? If you take off a 0, it's 29. Yes, 10% of 290 is 29. So minimum means we're going to take the 290 and lose 29 ohms. We're going to subtract it. And if you see in my first yellow highlighted band here, do I not show on the slide 290 ohms minus 29 gives us what? 261. But there's a faster way of doing this. The faster way is to use a decimal multiplier. 290 times 0.9. Do that on your calculator right now. Take 290 and multiply this by 0.9 and hit equals. Bam. What do you get? You still get 261, but it's much faster if you use the decimal multiplier rather than subtract 29. Now, how about the maximum? The maximum means we can take 290 and we're going to add the 29 back in. So 290 add the 29 is a bunch of keystroke steps on your calculator. You end up with 319 according to my PowerPoint. If, however, you use the decimal multiplier, when we're adding back 10%, that's 110%. The decimal for 100% is 1.1. So clear the calculator. You take 290 and multiply this by 1.1 and hit equals. Bam! Do you still end up with 319? Isn't that cool? And it's much faster. It's way more efficient. Here's the thing: when you're in front of your next prospective employer, and all of you are going to be moving from one employer, one company to another, so get used to practicing the interview process. And so during the interview process, they're going to be, you might be in a room with 20 other people, and they're going to watch how you do things. And some of those things that they're going to have you do may, in fact, be to calculate something. And those of you who can work smarter, not harder, will be the ones that will stand out in the crowd. You always want to demonstrate that you can work smarter, not harder. Let's take a look at the 5 band resistors, and I have this in the blue box. In the blue box, orange, gray, brown, red, brown, red. First band, second band, third band are the first 3 digits. Orange is 3, gray is 8, black is 0. So my first 3 digits are a 3, 8, and a 0. My 4th band represents what? Is my exponent multiplier, or what did I say? Number of what? Zeros. And that 4th band being brown, how many zeros am I going to add to the 3? Lord, people asking me, what link is for the meeting? I put it on, they're lost. So they will find it. I put it in Discord. And I also put it in announcements. They will find us. If they don't find us, too bad on them. And that's the other key. You know, to be successful in any endeavor, in any industry, you have to know where to find your answers, especially if they're given to you. Okay, so we have 380, and we're going to add a 0 to that, so that becomes 3,800. 3,800. Plus or minus 2%. Now you want to calculate the minimum. Well, what's 2% of 3,800? It works out to be 76. Minimum would be 3,800 subtract 76 according to my PowerPoint slide. Works out to be 3724. We're going to use a decimal multiplier. Right now, take 3,800 on your calculator, 3800, and multiply this by 0.98 times 0.98. And when you multiply this by 0.98, bam, do you end up with 3,724 on your calculator, which in proper engineering notation, we would round to become what? 3.72 kilo ohms, yes? And then finally, we have the maximum. The maximum, we could add back in the 76 ohms for 3,876, or take your calculator, 3,800, and multiply this by 1.02. That's adding in the 2%, and you end up with 3,876, which you will round in proper engineering notation to 3.88 kilo ohms. Okay, any questions about how to calculate minimums and maximums using a decimal multiplier so far? So here's the thing. I've only given you 2 examples out of 5 different tolerances, because you have, in the 5-band resistors, they come 1 or 2%, and in the 4-band resistors, they come 5%, 10%, 20%. So there's 5 different possibilities. I've only shown you 2. Well, what do we do about the other decimal multipliers? Well, this is another thing on the next slide you want to add to your notebook. Here we go. Mouse. Where's my mouse? Here's my mouse. Okay, cool. Here we go, my friends. This little table on the upper right-hand corner is what you want to add into your notebook. And when you think about what this is about, all these decimal multipliers will make sense to you. If we look at the pink box for a moment, the flesh-colored box for a moment, In the 4-band resistors, you have 3 different tolerances. You have gold, silver, and no band. In the 5-band resistors, you have 2 tolerances, and that is red and brown for 1 plus or minus 1% or plus or minus 2%. If you take a look at my table, and we take a look at gold, gold is specified at 5%, plus or minus 5. What is, when you walk into any store, what is 100%, and they give you a 5% discount? What's 100 take away 5? Isn't that 95%? And isn't 95% expressed as a decimal 0.95? So right away, right here, you save the step of having to calculate that 5% in ohms. You save yourself the step of having to subtract that 5% in ohms and subtract that, or add that 5% in ohms. You just use the decimal multiplier. How about 100% add 5%? If you have 100% and you add back 5% for maximum, won't that be 105%? And isn't the decimal for 105% 1.05? There you are. And that's how this chart comes about. All of these decimals, decimal multipliers, are easily determined just by adding or subtracting the percentage to the 100%. In the violet box, the lavender colored box, purple, whatever you want to call it, I give you a 4-band example and I give you a 5-band example. And I'm using decimal multipliers all the way. Let's look at the last one: gray, white, blue, red, red. Gray is 8, white is 9, blue is 6. Red tells you there's going to be 2 zeros, and then plus or minus 2%. So that works out to, on my line, 89,600 plus or minus 2%. How do I quickly calculate min and max? Just multiply by the decimal multiplier. Oops, I got the wrong one in here. I just realized. Too fast. I get to fix it. There we go. Hopefully my math was right. So let's double check that. So 89600 times 0.98, 87. Yeah, okay. So the calculation is right. I just fixed the decimal multiplier on the slide. Any questions about this? Because you have an exercise on calculating minimum maximum tolerances on resistor color codes, and that's part of this week's assignments. It's a 25-point exercise. So hopefully, let me go ahead and hit save. So this will save, and let me go ahead and save this also, save as, because I'm doing this in the form of a PDF as well. Save and replace that. Cool. Okay. All right. That has been saved. Go away. All right. Any questions before we move on? Okay. I'm going to close these PowerPoints for that. I will. So let's go ahead and do some calculator exercise practicing. So say for a moment, we happen to have V is equal to 18 volts, and R is given as 2.2 kilo ohms. And the question is, what is current? Okay, how much is the current? So if you recall, in Ohm's law, you have V, I, and R. So if we're current is equal to the symbol I, so what we need to do in this illustration here is cover up the letter I, and so I shows you the relationship between the 2 remaining quantities. So from here you should be able to derive I is equal to V over R. So far so good. Now we pop in 18 volts at the top, and we pop in 2.2 kilo ohms on the bottom. And here's where a number of students have a stumble in the middle of the road here. They key in 18 divided by 2.2 and call it a day. Can't do that. it's 2.2 kilo. So what are the keystroke sequences? What is the keystroke sequence that we need to do in order to achieve this? It would be, and here's the keystroke sequence. And it would be 18. And the key that you're going to use is divide 2.2. And then on the calculator that I specified for us, you happen to have an EXP key. Now, if you're not using this calculator, not to worry. On some calculators, you might see this key. It could be noted as a double E key. All right. On some calculators, it might be noted as a 10x key. So 2.2, and then you look up at your engineering chart, kilo. Kilo is what power of 10? Kilo is your 10 power. This would be 18 divided by 2.2 times 10 power 3 for kilo. So we have 2.2 exp 3. So by entering this sequence, you have put into your calculator 18 divided by 2.2 kilo. All you have to do now is hit your equal button. And when you do so, I'll go ahead and do it with this calculator. Let's see what we have. Put this over there. 18 divided by 2.2 exponent 3. And you want to make sure you see this on the display of your calculator, whichever make you're using. They all work similarly. 18 divided by 2.2. You better see some designation, a 10x something here or an E something here, 3. Without the kilo quantity in here, the answer is going to be erroneous. So we're going to hit equals. And guess what? This lands on in an engineering prefix on the side, on the right-hand side, tells you what it is. You should be able to see that this is a -3. Now, and so we would write this down as 8.18. And exponent -3, if you look on your chart, was milli. So you write this as a lowercase m, and you write this as a capital A. Very important. You use case, everything is case sensitive as you write it, okay? Very, very important. I've seen some people write things in a sloppy fashion, and they may end up writing, let's use something a little heavier than this. Here we go. They may end up writing 8.18. Well, that's how I write my M. Well, that's clearly an M. Well, that if I round it, that means a lowercase m. Well, if you write it at the same height as the capital A, it looks like mega. And so you got to set aside your personal style of how you write things and conform to the demands of the industry. And the demands of the industry are case sensitive. So back in the day, when you all were in grade school and they taught you how to write lowercase and uppercase, lowercase is going to be an M, and it's going to be written like so. And your amps is going to be capital, it's going to be written like so. And yes, scale is everything. So you have to have an engineering prefix with the appropriate electrical term symbol, okay? So any questions about this particular keystroke sequence and how this works on your calculator? You have a number of different options of how to do this. On some calculators, you might even have to hit the second function. There may be for a second function in order for you to engage the 10x. So it'll vary from one calculator to another. And as I've said, I will be happy to review your own calculator differences with ours on the second hour. I won't take any time now to talk about individual calculators, but this is a very, very good sequence. Now, let's talk about something else. I'm going to flip this over, and let's get a totally new sequence here. Let's do a sequential calculation. Let's do this. Suppose my V is equal to 5 volts, like what we have, and suppose the R, in this particular case, is 6.7 kilo ohms. And you are asked to calculate I equals question mark. So according to our friend Ohm's law, again, V, I, and R. The I calculates to be equal to V divided by R. This is equal to 5 volts divided by 6.7 kilo ohms. This is equal to 5 volts divided by 6.7 times 10 to the power of 3 ohms. So the keystroke sequence will be as follows. It will be 5 divided by 6.7 followed by exp 3. So we have the 5, which represents 5 volts. You don't have to write the V. 6.7 exponent 3, which represents 6.7 kilo. You don't have to write the omega in the keystroke sequence. And the next thing you do is you hit your equal key, and let's see what it is that you get. Question will go to Erica. Could you do this and give us what you calculate on your machine, please? 5 divided by 6.7 exponent 3. And what do you get? Erica, could you unmute your microphone? Do you have a calculation for us?
I got 4156.
Okay, could you read that again? So it would be 5 divided by 6.7 kilo, and then so you were a little faint at the very beginning of the sequence of numbers. Could you read that nice and loud into your laptop?
Yeah, 0.4156.
0.4156. Huh. Okay. Am I doing something weird here? Okay. So 0.4156. 0.4156. And we'll hang on to that. And let's see, Gregory Pella, can you give us what you calculated, please?
Yeah, I got 746.27.
I need more than that.
Yeah, I got it's UA.
Yeah, and what's the U? How do we pronounce the U?
Micro.
Micro, yes, okay. All right, so let me do this with you on my calculator. Hopefully everybody can see this calculator. So if you'll mute your microphone right now. So if you don't mute your microphone and you happen to make some noise, then what will happen is you'll snatch the camera view from everybody and we'll see your name or we'll see your face and we won't see what we need to be looking at here on our calculators. So we said 5 divided by 6.7 exponent 3. So if you review my calculator line, does it show 5 divided by 6.7 kilo? And then I hit the equal, and then you see over here, it's the calculator defaults into scientific notation, which is 1-digit decimal and followed by decimal point, and it shows us 10⁻⁴. That won't help us because we want proper engineering notation. So we get proper engineering notation simply by hitting the ENG key. So by hitting the ENG key, this automatically reshuffles the display and gives us the correct engineering, and the engineering works out to be 746.27, because we want to round to 2 digits after the decimal point always. So we look at that third digit. That third digit is an 8. That will compel us to round that 0.26 to become a 0.27 on our answer sheet. Now, our friend just called out 746.27, and I says, plus, and what else? So we have to remember on the far right-hand side of the display, we see a 10 power of negative 0.6. So you look up on your chart, negative 0.6 is the symbol that looks like the letter U, and it is like a cursive italic U. It's written like this. It's pronounced micro, and it's written in lowercase, and then you have capital A for amps. So this would be the correct way to specify the final result of your calculation in this sequence, okay? Now, let's give you something else to think about. Here's something else to think about. And let's go ahead and do it this way.
I have a question.
Please.
How come I'm getting a 750?
You need, well, you need to, what calculator are you using? Are you using our calculator?
Yes, I got the same one. What you using?
Okay, so this is what you need to do. Go back to the very beginning in the very PowerPoint, the very first PowerPoint from the previous week, and it shows you how to clear your calculator. So clear, so shift clear 3 all, and it resets everything. Okay, once it resets, it equals. Now everything has been completely reset. Then you hit mode once, hit mode again. You want to select 1 for degree. Clear. Then mode, 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 and then you see the little SCI, yeah? So you have to hit number 2 for scientific. So I hit number 2. And then it asks you here, how many digits? And in my PowerPoint, I says, if you're given an opportunity to fill the display with the full 9, you select the full 9. You didn't select your full 9, somehow you hit a 5 or something. So you have a limited number. Now you should see this number of digits on the display. This calculator is ready to do this calculation. 5 divide by 6.7 exponent 3, boom. It shows us a scientific value, and now if I hit engineering, it shows you all the digits I showed you previously, and you should be able to see all these digits if you reset your calculator.
Yeah, I got it.
Okay, cool, all right. All right, now let's go ahead, something more worthy of our time, and I say if I is equal to 746.27 microamps, and let's say V is now 300 millivolts. P is equal to question mark. So if we go back to our circle formulas, and I said most of the time we would be using the first power circle. We will occasionally be using the other circles, but most of the time we will be using the first power circle, and that was given as P, I, and V. Let me use a darker ink so you can see better. So P, I, and V. All right. So given, and I named this circle PIV, P-I-V for PIV. So if I'm looking for power, this particular circle formula suggests we put our thumb over the P. What's left between the I and the V? What's left is going to be, P is equal to I times V, yes? And that would be, right here, 746.27 microamps. I'm going to multiply this by the V, 300 millivolts. So the keystroke sequence, the keys are now as follows. Watch very carefully what the keystroke sequence is going to be. Somebody will be able to call this out. In fact, I'm going to call on a couple of people. I'm going to start this off as 746.27. And now my line says micro. So how am I going to key in micro? What keystroke sequence do I use for micro? Question goes to Kirsten. Could you tell us what would be the key after 0.27?
Can you hear me?
Yes, we can hear you fine, sure. So after the 746.27, what would be the next set of keys that I would punch in?
By keys, do you mean,
The buttons on the calculator.
oh, so,
Yeah.
okay,
How
really
do I?
embarrassing. I just remembered we had class, so I haven't done the,
Oh no, it's
I
okay.
haven't done this kind
All right, then I'll ask someone else. Let's see.
of bad.
Efrain, can you give us this one?
Yeah, I could. I think based on the calculator you guys are using, because I'm using a little different calculator, but it's
on
taking
ours.
your. Say again.
Yeah, based on ours.
Yes. So you take the 74627 times the 300 millivolts.
Well, we're not going to do that because we did not key in micro yet. We can't take the 746.
Oh, okay, yeah, sorry. I did that in my.
You
I'm
did
so
not
sorry.
pull the calculator micro. All right, so
Yeah,
let me take over the microphone. What we should have here has to be exponent. Okay, and then micro is what power of 10? If we look on the chart, micro is -6, yes? Milli is -3. Micro is the -6. Milli is the -3. So how do I key in a negative? I do not use the subtract key on this calculator. On this calculator, we don't use the subtract key. We have a change sign key right here. The change sign key is this little minus in parentheses. So it will be, this is my change sign key. And so it will be exponent -6. Now I'm going to multiply this by the 300 milli, but I have to key in 300. Now, how to tell the calculator milli? I have to hit my exponent one more time, exp, and milli is again a negative power of 10, but unlike micro, which was -6, milli is a -3, like so. Then I have told my calculator the information it needs to have. I can't just punch in numerals. I cannot punch in 746.27 times 300. That's meaningless. We have to punch in 746.27 micro, and we key that in as exponent -6 times 300 milli, and we key that in as exponent -3. So I will go ahead and do this with you, clear my calculator, and go ahead and punch in here 746.27 exponent, change sign 6, and now multiply this by 300 exponent, change sign 3. So have I put into the calculator this keystroke sequence, which was previously shown on this paper in red. All I have to do now is hit equals. And I'm going to do this off screen because I'm going to ask Luis, do you have a total for us? Do you have what that works out to be, my friend?
Yeah, I got 223.88 capital MW. That's should be megawatts.
Is it a +6 or a -6 does your display show?
Oh yeah, I got -6, so it should be microwatts.
Micro, correct, and watts is a capital W. Okay, and if I bring this back into view, you should be able to see 223.881 with a 10 power -06. And we would write that answer as shown here, 223.88 microwatts. Any questions on this quick review of how to input your values into your calculator so your calculations will work out properly? Any questions so far? Because what we're going to do from 7 o'clock on is just practice more of these, but I just wanted to show you the process. Very important in your notebook you write out the keystroke sequence that is specific to your calculator. If you're not using this calculator, if you're using this calculator, if you're using this calculator, other calculators, you need to write down the keystroke sequence that is specific to your calculator in your notebook. It will become second nature. After a weekend of doing this, it'll become second nature, and you won't even refer to the keystroke sequence because you'll become used to your own machine. It's like a new car. When you get a new car, you have to read the owner's manual to know where that button is and where this button is. But after a week, you know where all the buttons are, and you can operate your new car just fine. Follow? Okay. All right. The next thing I wanted to talk about was voltage divider formula. All right, so voltage divider formula, we have us a brand new circuit. And this is circuit EFGH. This will be circuit H. And what I have for us here is, let me go to a share. Let me go to a share. Oh, yeah, somebody typed in the number nicely. Thank you, Ephraim. I appreciate that. Yeah, the number is correct. Let's go, oh, let's find this one. And let's go to the specific slide of interest. Oops, come back here. Here. Okay, on Tuesday, and let me go ahead and share screens with you now. Share screen. And if my microphone does go weird on me, let me know. Hopefully not. Screen 2. Okay, can everybody see my PowerPoint? My PowerPoint is currently on digital multimeter. Give me a thumbs up if you can. Cool. All right, so we left off here on Tuesday showing you a digital multimeter used in a number of different functions. It could be used as a voltmeter or an ammeter or an ohm meter. And the voltmeter connections, these are very specific, and I will practice this with you in the second hour to our heart's content, but it does go to show voltmeter connections are very specific. You have to follow these to the letter. Ammeter connections are even more specific, and I said for our circuit F and circuit G, do not measure current. Do not measure current. Do not measure current. Did everybody get that? Do not measure current, because I will view current measurement with you next week. I don't want you blowing up your fuses this week accidentally, okay? So do not measure current. Then resistor measurements, and we showed you how resistor measurement works, and that you have to disconnect the voltage source. You have to make sure the polarity is not a concern. All right, now enter circuit analysis. Here we go. Pull out your calculators. And we have a simple circuit. It's 3 resistors. This happens to be R1, R2, and R3. This happens to be a 330, a 100, and a 220. And just with your calculators, because you have this PowerPoint already loaded in week 2 Canvas. This is currently existing in Canvas in its present format. So we have 3 resistors, and we have point A, point B, point C, point D. And we have these polarities. So let's study these polarities for a moment. Long plate of the source is positive. The short plate of the source is negative. It turns out that if you take a look at R1, the top of R1 being connected to the top of the voltage source, and listen to the verbiage, it shares the same polarity. So if the top of the source is positive and the top of R1 is connected to the top of the source, it must also be positive, which means the bottom of R1 has to be negative because the polarity is going to be opposite on the other side of R1. Take a look at R2. The top of R2 will be positive because it is closer to the positive side of the source. The bottom of R2 will be negative. The top of R3 will be positive. The bottom of R3 will be negative. So the top of R3 is positive. Top of R3 is positive. The bottom of R3 is negative. Do I have the bottom of R3 hooked up to the bottom of my source, which is also negative? So does the polarity of the source guide the polarities across my resistors? The answer is yes. How do we polarize resistors in any circuit? We have to look at the polarity of the voltage source. Okay, so far so good. Okay, so that being said, that's how the polarities work out. Now I introduced to you a new symbol here. This new symbol at the bottom of this hand-drawn schematic is called ground. And there's several different ways of drawing the symbol for ground, but I've drawn it this way. And ground, I will talk about in greater detail another time, but it is simply a common reference point. Think of it as common reference point. We'll come back to that verbiage in a little bit. Now, we introduced you to voltage divider formula, and voltage divider formula is a really neat formula. It is a fractional formula. In other words, we can calculate the voltage drops across each one of these resistors without Ohm's law. How do we do that without Ohm's law? Simply by looking at the ratio of the resistors. If I want the resistor known as X, I put the Rx in the numerator, R total in the denominator, and multiply that by my voltage source. So take a look at what I've done here is for VR1. VR1, I would use the value of R1 divide by R total. So there's my fraction, R1 divide by R total multiplied by the voltage source. What's my R1? 330. What's my R total? 650. Because if you add these up, you get 650. And if you go to divide, go ahead and, oops, silly me, I have to fix this. I got so excited doing this earlier. No, this is right. And then so 630 divide by 650 times 5. So everybody do that on your calculator. I'll do that also. So 330 divide by 650 and multiply times 5, then hit equals. Does your calculator fill with all kinds of numbers in the display? Okay, and as it does, remember, we have to round to 2 digits after the decimal point. So your calculator shows, if you can see where my face was, and if you can see the grid of your classmates. If you can't, it's okay, but your calculator should show you 2.53846154, bunch of digits. What's my third digit after the decimal point? It should be an 8. And that 8 compels you to round the 0.53 to become what? 0.54. So is everybody in agreement that our rounded answer for VR1 should be 2.54 volts? So far, so good? All right. Now, the next one is more interesting. R2 divided by R total. So clear your calculator and now do 100 divided by 650. 100 divided by 650 gives you some scientific thing, which you will fix by hitting your engineering key. And when you hit engineering, oh, sorry. I got too excited. Backup code. 100 divide by 650 times 5 volts. Boom. All right. Your calculator gives you some engineering thing, some scientific thing. You're going to hit engineering. And when you do so, does your calculator show you 769.23, 10 power negative 3. Do you see a 10 power negative 3 on the far right-hand side? Yes. Don't get so excited with the big digits you forget to look at the 10 power negative 3. That has happened on the number of papers that I have received so far, and that only gets you half credit. If you miss that 10 power negative 3, it's a big miss. And so on the answer sheet, it has to be shown as millivolts. So are we cool with using voltage divider formula and generating 769.23 millivolts? So far, so good. Thumbs up, yes. Okay, all right. Now, the last one is an easy calculation. You end up with 1.69. You can go ahead and verify that on your own. I'm going to write these values on the side, 2.54. 769.23 millivolts and 1.69 volts. I'm going to write those on the side because I'm going to need that in a moment. Any questions about voltage divider? All right, now, when we go to the next slide, I'm going to measure this thing. I built it, and now I'm going to measure it. I want the voltage across R1. We calculated 2.54, and now when I go to measure this, and you can see on my voltmeter, I'm using the little guy, I've got the dial set to 20 volts maximum, okay, because these scale markings show you the maximum of what the voltmeter is going to read at this moment. So I have it at a maximum of 20 volts because this is under 20, and it shows me 2.50. Is that pretty darn close to my calculated 2.54? Pretty darn good, okay? If I go to measure the next one, we calculated 769.23 millivolts on my multimeter, and I have this, I can select scales on this multimeter. This is not an auto scale multimeter. And on this multimeter, if I set this to the 20 volt maximum scale, I'm getting a 0.75. 0.75 is not going to cut it for me. If that's all I have, and I can't, if you're using if you're using an auto scale digital multimeter and it doesn't show you anything other than a decimal, then you'll have to interpret that using your calculator into proper engineering notation. You're not going to write down 0.75. It'll be 750 millivolts. But interesting, on this digital multimeter, I do have another scale. I can go to millivolts. I can go switch this dial from 20 volts to 2000 millivolts, which is what I've done here. So for greater accuracy, I've changed the scale of my digital multimeter to 2000 millivolts max. And is this reading something under 2000 milli? It's reading 757 milli. Is this more accurate? Does this show greater resolution than my decimal value on this scale on the left? Yeah. And take a look at my connections. I'm using little hooks. I could use the probes. I can use anything I want, but I happen to have hooks, so I'm hooking onto the resistors, and I'm specifically across the voltage across R2, and that's pretty good. I expected something close to 769, and I got 757. Done. Now the last guy we calculated 1.69, and guess what? I go back to the 20 volt scale. I'm measuring across the third resistor, and I've got 1.66 compared to my 1.69. I'm a happy camper. But I want you to look at something very carefully on my circuit build. Is my red lead physically hooked up to R3? No. My red lead is hooked up to the bottom of R2. Is this a legitimate measurement of R3? The answer is yes, because the bottom of R2 is connected to a red jumper and then connected to the top of R3. Point C is actually can be measured at the bottom of R2 as well as the top of R3. So that is a legitimate connection for my voltage at across R3. Now here is something interesting, and I will depart from this for a moment. Let me grab another paper and show you the next set of measurements and what you should be looking for and understanding. And that is this. Let me go ahead and fold the paper. Go back to my unshare this screen. Unshare my mouse. Stop share. Okay. And this is in focus. Let me bring this down a little bit more so we can see this in greater detail. My camera lens. My camera lens is over here. That's good. All right. Very nice. Okay. New piece of paper. So my new piece of paper, the circuit that I had for you was shown this way. A node, I have a resistor. This is my 330 ohm resistor. I have a node B, and this is my, actually I'm going to change this. I have a point A, I have a resistor, And I will write 330 in here, ohms. I will write point B in here, another resistor. This is, what did I say that's what it was? This is 100 ohms. This is 100 ohms. 100 ohms. So that's point B. This is point A. This will be point C. And then I have a third resistor, and this will be my 220 ohm resistor. This was my R1. This is my R2. This is my R3. And down at the bottom of the circuit, I have a point D, which I've attached a ground symbol. And then we pull these wires over here, pull this wire over here, and come down to this. And we polarize this. We'll go ahead and polarize this guy. And we said that the polarization was very specific. The polarization is completely dependent upon the plates of the voltage supply. I happen to have the long plate on top, it must be positive on top. I have the short plate on the bottom, it must be negative on the bottom. The top of R1 is attached, if you follow the wire, to what polarity of the voltage source? The top of R1 is attached to the positive side of the source. It must be positive. The bottom of R1 is going to be negative. The top of R2 is going to be positive. The bottom of R2 is going to be negative. The top of R3 is going to be positive. The bottom of R3 is going to be negative. And is this negative matching the attachment to the negative side of the source? Yes? So far, so good? Okay. Now, what we just calculated in the previous slide, was a voltage from here to here. Our VR1 was calculated as 2.54 volts. And across here, from here to here, my VR2 was calculated as 769.23 millivolts. And my VR3 was calculated as 1.69 volts. So this is a reiteration of what we spoke on the previous slide screen that I shared with you. I've just simply written these values down on a schematic for reference, because what I'm going to talk about next, why do I put these letters here? And if I show you this, if I asked V at point C, and I ask you question mark, I show you the quantity we want to measure is a V, and I show you a single letter. Well, what do you do with that? Well, it turns out you whip out your handy dandy multimeter. So there's your handy dandy multimeter. You get out your red probe, and oh, but wait a minute. Voltage is always measured between how many points? 2 points. What is the single letter business? Well, you'll often see in the literature voltages requested of you specified to a single point. When you see this, that means you will put the red probe on point C, and the black probe will always go to our common reference point. Ground is our common reference point. That's where the black probe will go. So let me just go ahead and reiterate that with you. GND is equal to something called ground, and that's equal to common reference point. And so if I go to put my red probe here, and I go to put my black probe here, what value of voltage is physically between these two probes? Isn't it VR3 that I've written in green? Should I not be able to measure at point C 1.69 volts? How many people agree that that's what I should be measuring at point C with respect to ground? Yeah. And so what I'm going to do is I'm going to hook up this puppy. I'm going to power this guy up and bring this guy out into the view. And let's see, I'm going to hook up the black probe to the bottom of the circuit, which is point D, which is my ground. And I'm going to hook up this at point C, which is right here, and turn this guy on. Lo and behold, what's my digital multimeter say, if I can get it out of the glare of the light? 166 volts. Pretty darn good. Yes, it's close enough to this. We're pretty happy with that. Yes? All right. So here is the next lesson to learn. When you see single point, when you see single points like this, VC, this means voltage at point C, and here's the phrase, with respect to ground. That is a very common phrase. So when you see voltage specified at a single point, you will read this as voltage at point C with respect to ground. So how about if I were to show you this guy here? How about if I were to show you, well, how about VB equals question mark? How will you read that? So the question goes to Chisamaga. Chisamaga, unmute your microphone if you would. How would you read V sub B compared to what we have in the previous example? Chisamaga, could you unmute your microphone?
Would it be the voltage at point B with respect to the ground?
Voltage at point B with respect to ground. That was spoken like a seasoned electronic technician. That's exactly how you read it. It's exactly how you pronounce it. It's exactly how you speak it. Voltage at point B with respect to ground. And so that means on my schematic, I'm going to take my red probe. I'm going to put my red probe at point B and put my black probe at point, well, ground in this case. Now, what kind of voltage do I have between these two? Wow, I've got two voltage drops between these two probes, do I not? I've got the voltage drop of VR2 and the voltage drop of VR3. So how can I predict what should be measured between these two probes? Maybe I should do what? Anna, what do you think I should do? What should I do for a prediction, Anna?
You could add them together.
Okay, how many people agree? We can add these guys together. Yay, that's what we're going to do, my friends. We're going to add these two guys together. So you'll whip out your friendly handy dandy calculator and you're going to key in 769.23. How do I key in milli? Don't forget to key in milli. Don't just go punching in numerals like some of our friends have done. Milli is exponent what? -3. You got to key that in. Then you're going to add that to my 1.69. And when you do so, what do we get? We should have something that we would round off to be 2.46, yes? 2.46 is what we should be, or should be our target if we want to measure from B to ground, 2.46 volts. Let's see if that works out to be true on the circuit board itself. I'm going to put my red probe at point B, put my black probe at ground, and we expect something close to 2.446. What do we have? 2.42. That's reasonably close. Again, my power supply is supposed to be 5, and I think the way I have it loaded, it's not a full 5 to begin with. But that is really good. We expected 2.459, which we will write down 2.46 volts, and we measure something 2.42, which is great. All right. Now, one more thing. I will depart from the circuit. Suppose you see now a new designation, VCA equals question mark. What on earth do you do with this? So question goes to, let's take a look here. Hey, Harpreet, welcome. What do you think we should do with this, Harpreet? Unmute your microphone. Tell me what we should do with this.
Should we measure all the way across?
I need something all the way across what? I need something more specific.
Point A all the way down to the ground connection D.
Well, what did I write down?
So voltage drop across CA.
So here's the thing. When you see two letters, when you see one letter, it will always be with respect to ground. When you see two letters, the two letters tell you exactly where these two probes need to go. The first letter gets the red probe. The second letter gets the black probe. Are you following me?
Yes.
First letter, yeah, everybody. So first letter gets the red probe, second letter gets the black probe. So watch what happens. I'm going to put my red probe on my paper at point C. I'm going to put my black probe up here at point A. Do I have a quantity between these two? Yes, I do. I happen to have two voltage drops. I have a VR1 and I have a VR2. But something interesting, we already know if I have two voltage drops between these two probes, we're going to add them together. However, look at the red probe and look at the black probe. The red probe is the one that we said on Tuesday always sends polarity. As we move the red probe towards the black probe, whatever polarity this guy sees first is the polarity of the voltage. So as I move my red probe towards my black probe, what's the first polarity it's going to see? Negative. So the red probe will read a negative 769.23 millivolts across the second resistor. And then we're here. Now, as we continue moving the red probe toward the black probe, it sees a negative symbol again. It will see a negative 2.54 volts. So the difference of potential, the voltage between C to A, has to be determined this way. This is going to be equal to negative 769.23 millivolts, and I'm going to add that to a negative 2.54 volts, 54, giving me a total of, I'm going to have to do it this way, and on the calculator, clear. So change sign, change sign 769.23 exp negative 3, and I'm going to add that to change sign 2.54 equals. What do I have on the display of my calculator? I should have a negative 3.31 volts is how I would round that off. Did everybody follow what I did? If you didn't, review the YouTube when we record this and put this on YouTube. But you should end up with a negative 3.31 volts according to your calculator, according to how we read from point C to A. That being said, here comes my schematic, here comes my circuit, and I'm going to put the red probe at point C. So my red probe will go to point C, right there. And my black probe will go to point A, which is at the top of the circuit, right there. And I expect something close to negative 3.31. What does my digital multimeter show me here? How about that? That's pretty darn good. You should have a negative symbol in front of the 3.31 on your answer sheet. Your probes should be set up this way, and your digital multimeter better show a negative sign on the far left-hand side, something close to the 3.31. I'm very happy with 3.26 volts. So this is a more in-depth analysis of how to measure voltages at specific points with respect to ground, and how to measure voltages between two specified points. Always remember, red probe goes to the first of the two specified letters. The black probe goes to the second of the two specified letters. If you only specified one letter, then the red probe goes to that letter, and the black probe must be with respect to ground. Any questions about this expanded discussion here? Okay, then go back to my share one more time. And what I've got for your viewing pleasure as we wrap this first hour up, we're a little over, but that's okay, is my voltage. Don't have any room for my mouse. Get rid of all of this. Now I have room for my mouse, yes. All right. The voltage from B to C was 2.42. And if I reverse that, if I put this D to B, see voltage D to B, you see this VDB. First letter gets the red probe, second letter gets the black probe. So my red probe goes to point D and my red probe goes to point B. This will be a negative 2.41 as opposed to the previous, flip the probes around, B to D instead of D to B, I have a positive 2.40 something volts. And if we do what we just measured together, my friends, from C to A, red probe on C, black probe on A, negative 3.26 volts. This is in your current updated version 2 PowerPoint in Canvas week 2. So all of these slides up through slide 31 is in here. And I've covered my objectives. So my objectives were to talk about resistor tolerances, so you can get through that exercise, engineering prefixes, circuit build. There is one more thing I want to help you with, and that has to do with your work assignment. Your work assignment has a interesting question as one of many questions. Let me go to this link. All right, I'm done with the PowerPoint. Save, thank you very much. And let's go here. And let's go two things. In week 2, you have the PowerPoint, you already have one YouTube. There also happens to be in this first folder the audio transcription. So everything that is spoken with you and I during the course of these recordings is all there. And all of that is archived for you because we have different students with different learning challenges. I have a learning challenge. You all know that I'm dyslexic. And so I find it helpful at times to review the text of what is spoken. And so the text is offered here as audio transcript. And in the deliverables. So in the deliverables, I've also, for the PowerPoint as well as the deliverables, I've put this in as both PDF and Microsoft Office. So PDF is universally available and openable to just about everybody. And let's see, here's the PDF. Click home. You happen to have this week 280 points possible, and there's a 25-point bonus exercise which you will find in the in Canvas. That is completely optional, but if you play with that particular guy for extended VIRP calculations, that's worth an additional 25 on top of your 280, but all your deliverables are pointed out here. And there is, on your online assignments, the biggest point one is the 120 points there, so don't miss out on that. But you have 50 points of homework questions, review homework questions. So where do you find the 50 points of homework questions? That is found, you'll find that the deliverables list is in the same sequence as all of these folders are here. So homework questions. So if I go to click on this guy, it'll show the link to your homework, and then you upload this. This is worth 50 points. Homework looks like is this guy here, and it's really based on a lot of the theory that we had discussed in the previous week up through now, and you just fill this in. And something that was very interesting is this one, number 9. Number 9 shows what happens if the switch is open, what happens if the switch is closed, what happens if you're measuring voltage on a bare wire. So it's showing you 4 different multimeters. And it's asking you, you need to think about what this is going to measure. All right, so we have a closed switch voltage measurement, we have a wire measurement, we have a source measurement, and we have a load measurement. Let me answer that question for you with a real circuit. And the real circuit will be the one in front of us. Here's the one in front of us. And I'm going to be measuring some values for us. So I'm going to put this on 2 volts. And if I want to measure across the voltage source from the top to the bottom, that is from point A to point D, yes? Isn't point A attached to the top of my source? Isn't point D attached to the bottom of my source? So if I go to set this at the 20 volt maximum scale, and I go to hook up my black probe at the bottom, and I go to hook up my red probe at the top at point A, this is equivalent to measuring my voltage source. And my voltage source is supposed to be 5, but because this is a budget voltage source, it's going to be pretty close to 5, and it measures 4.90 in this particular case, and I'm happy with that, knowing that there's going to be some tolerance on the power supply. So I get 4. So across the voltage source, I expect to see the predicted value. Now the other thing is, so what do we expect across a load? Well, we expect a 2.54 across the first load, and we measured 2.50. So that when you measure across a load, you have to put 1 lead on the top of a load, 1 lead on the bottom of the load, and you have a prediction, and you look at your measured comparison. Another measurement was on the wire itself. Do I have a wire traversing the top of the circuit and the bottom of the circuit? I have a jumper here and I have a jumper here. If I try to measure the voltage across the jumper, well, let's go ahead and do that. I'm going to hook this guy up here, and I happen to have a pin, and the pin comes in your kit in this format, and I happen to have just snipped off one of these guys. So I'm going to take this pin and I'm going to jam it into the board, the other end of the wire. And now I'm going to hook up my black lead on the wire. Now, how much voltage do we expect to see on the wire at the bottom of the circuit? We expect to see nothing. Do we see nothing? It shows us 0, 0, 0. Interesting. Well, that was the bottom of the circuit code. That's ground. We don't expect anything at ground. Maybe yes. I'm going to put this at the top of the circuit. I'm going to put that little black jumper guy there. And I'm going to hook up A over here. And I'm going to hook up to this pin over here. And I'm measuring across that orange wire at the top. Whoa, I still get 0. So when you're measuring across a wire, you're measuring no resistance. If there's no resistance, there's going to be no voltage drop. And it should be 0 on any wire. The only time you're going to have voltage is if there's a difference of potential, as evidenced across R1 and any of the other resistors. Okay, so this might help you out on that homework exercise. One thing that wasn't asked of the homework exercise, and this is something very important for you to know, how much voltage will there be when the circuit has an open in it? Meaning, if I go to yank this wire at the top, I now move this jumper out. I no longer have a jumper that connects my source to point A. And I'm going to try to measure the voltage here. How much voltage am I going to measure on an open in a series circuit? Basically, what I've done is I've broken the wire at the top of this circuit. What do you think we're going to measure across that open? Think about that. You should measure the entire source. Here we go. I'm going to purposely hook it, reverse connection. Do I have the source voltage, my 4.9 some odd volts, across that open? Yes, I do. And I happen to have negative only because I put the leads this way. Well, if I put the leads this way, there, and there, I still get my source voltage, but now it reads positive. So there's where an open. Say, well, hey, code, that's at the top of the circuit. We figured it should be the full voltage at the top of the circuit. I put this guy back in, pull out my pin, and I'm going to yank out one of these side jumpers. I'm going to yank out the side jumper at point C. If I yank out that side jumper at point C, have I created an open between the second and the third resistor? Look at that carefully. There's an open. There's no connection here right now. If I yank this guy and I put in my LED, remember we have LEDs only at the beginning of our circuit builds just to make sure things were working properly. So just move it to you. I will go ahead and pop this back in. So if I put the jumper back in, does my LED light up? That shows me I have a complete circuit, yes? I yank this little jumper wire. I no longer have a connection between the bottom of R2 and the top of R3. I have what's known as an open. I've broken the circuit open. What is my voltage measurement across an open? Well, let me connect this to one end of the open, and let me connect this to the other end. I expect to see the voltage there. I expect to see the voltage source, which I do. I have broken the circuit open, I'm measuring voltage on open, and I get 4.9 and change voltage. So that's the last revelation I wanted to share with you about a simple series circuit, what kind of voltages we have at single points with respect to ground, what kind of voltages we expect between two labeled points, what kind of voltage we expect across an open. This is what we expect. Any questions, my friends? That concludes my first section of our required time together. All this is been recorded. And so now I want to open, I need to take roll. So let me go ahead and pause the recording. Thumbs up if you can see my share screen. It's a classmate's paper. Good, okay. So if we take a look at the efforts done by this classmate, the very first calculation, this is one of the homework examples. We have 18 volts, 980 ohms, calculate the current. And so when we go to take 18 and we go to divide by 980, so 18 divided by 980, you end up with a scientific thing, and then you hit engineering. What you all should have on your calculator is different than what this man wrote down. The numerals are very similar because in scientific notation, which was the very first display, 18 divided by 980, the scientific notation, the big numbers on the calculator shows 1.8367. So if you look only at the big numbers, it's very plausible you would round this to 1.84. However, the devil is in the details. And in the calculator, on the far right-hand side, was a power of 10 of 10 negative 2. First of all, that's not engineering. Second of all, you can't ignore it. So you use your engineering key, and it works out to be 18.367, which you will round to be 18.37 milliamps. So he wrote down 1.84. So this is a very, very common bump in the road. And let me disconnect my power supply, disconnect my leads. set this guy aside. Set that guy aside. Okay, and let's just look at the calculator. So here's our calculator. And as we said, it was 18 and divide by, clear, 18 divide by 980. And on this particular calculator, it lands us with scientific notation first. We should observe several things here. We should observe that it's 1.836, and you look at the power of 10, that's 10 negative 2. So clear, this is scientific notation. This is not engineering notation. Our classmate ignored this, looked at the big numbers, and put down 1.84. Can't ignore what's happening in this right-hand corner. So if we observe what's happening in the right-hand corner, we see 10 negative 0.2. That's not a multiple of 3. You know, the exponent's not multiples of 3, like mega, kilo, giga. All of those are 10 power multiples of 3. This is not. So what do? You hit your engineering key. And the moment I hit engineering key, this will shift power. The decimal point will shift position. Boom. We now recognize this is proper engineering notation. It is a 10 power some multiple of 3, in this case a negative 3, and we look at our chart and we see that that should be milli, and then the numerals instead of 1.84 now are properly rounded off as 18.37 milliamps is what we should have. Okay, so I point this out to you as a very common stumbling point when you go to do your calculations and you're keying in values. Very important, you do not forget to key in the prefix powers of 10, and very, very important, you don't ignore what happens on the lower right-hand side of your calculator. Does anybody have different calculators that they're using you would like for me to review how to do things on your specific calculator? Anybody have a Casio that they don't know how to use or would like a little explanation? Anybody using a Sharp that they would like to have an explanation what keys they should be hitting? I'll be happy to use this time to help you out. Okay, I guess most of you happen to be using the recommended calculator, which is hallelujah. Or if you are using a different calculator, such as, in this case, a Hewlett-Packard or a Sharp, these are great little calculators. You know and have found your way around how to key in the powers of 10 appropriately. So on this particular calculator, I turn this guy on, and if I do the same exercise, I do an exercise we did earlier, this one here, which is good, 746.27 exponent negative 3. So this would work out, once I clear this, 746.27. Now my EXP key is this guy here, times 10 power of x. And what my power of x is change sign 6. So I will find my change sign key right here, and 6. Now I've keyed in the micro. Sorry. Now I have keyed in the micro. And do a quick focus. There we are. Now I've keyed in the 746.27 micro. And now I'm going to hit times 300 exponent negative 3. So it would be 300. And on this particular calculator, it's the 10x key. And change sign is here. It will be 3. And then I will hit equals. And when I hit equals, I get scientific notation. And I recognize that because on the far right-hand side is 10 power negative 4. And it's a single digit in front of the decimal point. So fortunately, on this particular calculator, I have an ENG key. Touch the ENG key. Oops, I hit the wrong key. Silly me. Anyway, if I hit the right key, ENG, which was this guy here, I will end up with the 223.88 micro. On this particular calculator over here, you happen to have an EXP key and it's spelled out. So this would be 746.27 EXP, and then the change sign key is here, 6, and that's how you key in the micro. So very important on your own calculators, if we're not using the specified one, you find your method, you write out the keystroke sequence on your notebook the same way that I've written the keystroke sequence in our previous notes earlier this evening. Then you can jump in on those exercises. The circuit F, as I said, circuit G. So circuit G was this guy here, and circuit G does require you to put in the labels, and the labels are very important because that will be part of our next week's lab. Next week's lab will engage us in determining voltages at various combinations of points. So when you go to build, you build your circuit F first, get it done, take the picture, do the measurements, there you're all happy with it. Then you go to build your circuit G. Circuit G is built, put your little labels around it, do your measurements. Do not tear this apart because we're going to need this for next week in its entirety when we do voltages at very specific points. So we will do a VA, we will do VB, VC, V, and we will go from F to B and D to G, and we'll do various combinations of voltages. So keep this intact, okay? Any other general questions I can answer for you?
There's one question on the Ohm's law and Watt's law on question 7. I'm kind of stuck on that one.
Ohm's law, Watt's law, and question 7.
Yeah, the exercise.
Oh, the exercise sheet, not the practice sheet. Okay, let me get that up because there are two different ones here. And let's go to here. And that would be week 1 and week 2, rather. Ohm Watt exercise. Cool. Let me open that up. And which number was this? Number 7, did you say?
Number 7.
Okay, cool. So number 7 reads out this way. So number 7, and it goes to read what increase of current, what is the increase of current when 15V applied to, it looks like 10,000 ohm rheostat which is adjusted to 1,000 ohms. Okay, that's a really good question. That's the one we're referring to, yes? I'm so happy you asked that. I'm so happy you asked it. And the reason why I'm so happy you asked that is because last week, when we were doing our circuit builds, I introduced you to a device known as your potentiometer, and it was a little blue knob that we were able to turn that was able to make ohm adjustments, yes? Remember that?
Correct.
Okay, so that potentiometer is in large scale, this guy right here. This is a potentiometer. It happens to have a physical knob attached to it, and I can rotate it and spin it around. And this is very similar to the type of knob that you'll have on an oven door or whatever. It changes the resistance. And a potentiometer happens to have 3 pins, all right? So, and this is part of the background of this is in your reading. So let me go ahead, pot equals potentiometer equals 3-pin variable resistor. And the schematic symbol for that guy is here. I've drawn this for you before. I'll do it again. Here to here. And this might be point A, this might be point B, and this might be point C. And when so that's what a potentiometer is. A rheostat is this. Rheostat can be drawn a couple of ways. what I'd like to do with the rheostat is, so far it looks like a potentiometer, yeah? But what I'm going to do is I'm going to short this wire and then this wire right here, the wire from here to here. So now my point A is still A. I'll do that in black. My A is still here. But now point B, and this is point B, C is gone. Because these are electrically the same point, yes?
Yes.
There's no more point C. So a rheostat, what I've done is I've taken the potentiometer and I rewired to be a 2-pin variable resistor. And that's all a rheostat is. It's taking this guy and connecting 2 pins together so that these are common to each other and I have a leftover pin. So I've taken the 3 by putting this wire in between. There's no longer point C. This point and this point are now electrically the same. Now it's a 2-pin variable resistor. So this is what a rheostat is. So what they say is, what's the increase of current applied to a 10,000 ohm rheostat that later is adjusted to become this? First thing you got to do is you got to calculate the current. So if we go back to our friend, over here. Ohm's law, V, I, and R. It's a horrible V, sorry, VIR. So I is equal to V over R, yes? So initially, we have 15 volts over 10,000. Can we calculate the current of that guy right now, please?
1.5 milliamp.
Mm-hmm. So 15 divided by 10, 10,000. So double check before we hit the equal key that this is exactly what we want. 15 divided by 10,000. Hit this, and we end up with, you're right, 1.5 with a 10 power negative 3. So it works out to be 1.5
milliamp.
So far, so good. All right.
So good. Yes.
So now it's going to be what? It's going to be adjusted. It's going to be adjusted. So our R is now going to be different. You still have 15 volts, but this is now 1,000 ohms. So now you recalculate this guy. 15 divide by 1,000. Yeah, double check the calculator, make sure you key in exactly what you want. And then we hit equals. What is my, oh, and you get some scientific value. So what do you do when you see some scientific value? You hit your ENG key. Now in proper engineering, whoa, we have 15 milliamps. And so the question here is not what either of these are. The question is, what is the
increase?
Was there an increase between where it started to where it is now? Yes. So the increase is equal to 15 milliamps minus the 1.5 milliamps that we started with. The increase must be 13.5 milliamps. Does that help you better understand this question?
Yes, it did.
Cool. And hopefully that would be a benefit to our other classmates who might be sharing the same struggle. That's not calculus. This is just basic middle school math. And the key thing is reading what the objective is. The objective is increase of current. So in order to find the change of current, you have to find the initial current, you have to find the end current, then you can find the change of current and the increase where it was an increase of 13.5 milliamps, which is great. Good job. Anybody else happen to have any questions?
Thank you.
You're very welcome, my friend. Good question. Anybody else have any questions that you would like to have help with? And let me say this, if you run into a situation after we shut down for this evening because and you, oh, I should have asked him this. Oh, I should have asked him that. Understand, you can always throw questions at me through Discord. That's the fastest way to get something in my face. You can punch it into Canvas. It'll take a little longer for me to see it, but I will eventually see it. But the fastest way for me to see anything is we have a tool called Discord. It's on my phone. It alerts me. Now, just because it's fast that I can see it doesn't mean I'm equally fast in responding. I might be in the middle of something. I might be mowing my lawn. I might be washing my car. I might be in the middle of something. But the fastest way for me to actually see a question from you, shoot it into Discord. And if you don't want it to be in the general Discord window where everybody sees, oh, this guy's always asking questions, go ahead and ping me separately in Discord and I can answer you discreetly. Or you can put it in the general box and I can still say, could you answer me privately? And I will be happy to converse with you in Discord privately. So that will not ever be a problem. So if some question arises after this evening, don't sit there and huddle through it. Oh, here's the other thing. You can throw the question into Discord as a general question. And what I've seen is a number of students have jumped in there and helped each other out. There was a general question and boom, somebody else helped somebody else what that is. And when I see helpful assistance like that, that is worth bonus points. That if there's a question that's asked and somebody is helpful in helping that person, not giving them the answer, like, oh, the answer is blah, 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 but showing them how to get the answer, that's worth bonus points because that is building up a culture of helpful assistance that we want to foster for all the time that we're together. We're not competing against each other. You are not competing against each other. You're competing against a standard. And the standard is, here's the objective, here's what you need to learn. Can you achieve that standard? And the standard earlier this evening was, can you master the keystroke sequence and not forget your engineering prefixes and not forget to put them into the calculator and also not forget to read them off the calculator in those little corners of your screen, okay? So those are the things that you are to master, and chatting with each other on Discord is a really helpful, friendly way of helping each other out. Any other questions for me?
I have a quick question. What's going to be our first test?
You're going to see it next week. You're going to see it after. You will have a quiz first before you have a test. So you will see it next week. Good question. And we will be doing this live during the time we're together. It'll be I don't want to chew up so much of our 3 hours on Tuesdays with an hour-long test. That's not going to happen. You'll have a paper that might have 5 questions on it, and you're going to plow your way through it and submit your answers. And yeah, it'll be quick and fast and easy as long as you've been doing the things you've needed to do along the way. Did that answer your question, Abbas? Good question.
Yeah, thank you.
Thank you. Any other questions I can help you with? All right, my friends, I see some people have already signed off because they didn't have questions. For those of you who have hung in there and persisted, I commend you, because generally what can happen during this second part of our Thursday evening is somebody has a question. Oh yeah, I thought about that, but I didn't raise my hand. And you'll find that the time we spend together is hopefully very helpful to you. So on that note, I'm going to sign off now, and I wish you all a marvelous weekend. Be mindful of the engineering prefixes. It's something that you can conquer. It's not hard. The math is not hard. It's like baking a cake. The first time you bake a cake, it might not come out well, but you keep practicing that recipe. You use all the parts of the recipe. Don't leave out the eggs. Don't leave out the flour. Don't leave out the milk. You need those parts just like on your calculator. You need that engineering notation. You need the EXP key. You have to hit the engineering key. Don't leave out those parts. So as long as you follow everything that I have asked of you to do, you should be pretty successful with everything that we do. So I will say, have a lovely weekend, and I will sign off now. Adios.
Thank you.
Thank you very much, my friends.